In the scene that you've just witnessed, you saw, among other things, an example of something moving. We're going to concentrate on a few aspects of this kind of motion by taking another ride in another car, a somewhat less violent ride, and moving from some point like this, starting from rest, speeding up, slowing down, speeding up, slowing down, and so on, and finally coming to rest at some point like that. And we'll measure three things: distance, speed, and acceleration, all as a function of the time t of the trip, in terms just of these three quantities for every instant of the time from here to here. Finally, we will look for a relationship among these three quantities, and we will find one. We will find precisely how they're connected with each other. Kinematics is the study of motion. We're not going to be concerned here with friction and other forces, with power, fuel consumption, and so on. As a matter of fact, to get some understanding of these things, one has to begin with kinematics. As you go along in this course, you'll find that you refer again and again to the concepts of kinematics because they're essential to almost everything that happens in physics. And now let's have a look at the apparatus that we'll need to measure these three quantities. This is the car that I shall be driving during my attempts to get our measurements. We've also been able to borrow a few miles of partially completed, unopened highway, where we'll be able to work without being disturbed. All of our measurements of distance, speed, and acceleration will be derived from the rotation of this wheel, on which we've mounted a certain amount of electrical equipment coupled to the wheel through these gears. The signals from the wheel are brought up to these three instruments. These are devices for plotting curves on graph paper. If we regard them for the moment simply as meters of some unfamiliar kind, we can learn about how they work by looking at their response to the various motions of the wheel. For example, this is the distance meter. Notice that the scale is laid out in tenths. These are tenths of a mile. Now notice what happens when I begin to rotate the wheel. If you watch carefully, you'll notice that the meter slowly rises. Of course, it doesn't go very far. It takes about 100 turns of the wheel to go a tenth of a mile. And now the wheel has stopped and the meter holds its reading, just like the odometer in a car, which registers miles. Now let's look at the speedometer, which is this one here. It's calibrated in miles per hour here, 10, 20, 30, and so on, and also for convenience in miles per second. For example, 1,000 hour corresponds to 0.010 miles per second. Now the speedometer will read like this as the wheel turns. When the wheel stops, the meter comes back to 0. This is just like the speedometer in your car. And now let's look at the last meter on the bottom, which is an accelerometer. Now this is something you won't find in your car. The unit is miles per hour per second. It reads the rate of change of the speed. Notice that it has positive and negative readings. It will read positive when we speed up and negative when we slow down. For example, if I increase speed at the rate of 2 miles per hour per second, I will read this, and so on. Now off the wheel, like this. Notice that as it speeds up, I get a positive reading, and as it slows down, I get a negative reading. And of course, when the wheel stops, it reads 0. Now, I'd like to point out that we want to make all of these readings as a function of time, and so we'd like these pens to move across the paper at constant speed. I can do that this way. Notice that the pen is moving. It will write a line like that, and it moves at the rate of 1 inch in 10 seconds. Here's 10 seconds, another inch, 20 seconds, and so on. And that finally, when we take our data, we can use the line being drawn on the page instead of just the visual indication of the position of the pen. So now we're going to take our wheel, hitch it back up, and start calibrating the three instruments to see if they work. First, let's look at the measurement of distance against time. So far, of course, we haven't gone any distance. Now, let's start. And I'm going to come to rest next to a marker, which is the beginning of our track. Notice that the curve has leveled out, meaning that we've stopped moving. And so now I'll take off. And further down the track, there's another marker, which has the mark 0.3, 3/10 of a mile. These marks were laid out by the surveyors who built the road, and we have simply taken over their markings to give us ours. Second marker is now in sight. I'll slow down and come to rest next to it. Here we are. 0.3. All right, now I'll turn off the meter, like this. Pen stops moving. It leveled out again when we stopped moving at the second marker. Now let's see what we've got. Here's where we were at the first mark, and here's where we are now. Let me take the difference, coming from the bottom of that line to where the bottom of this one was, is there. Now let me read this off on the graph. Well, it looks like 3.02 inches, which corresponds on our scale to 0.302 miles, and that's satisfactory agreement with our markers. Now our next step is to check the speedometer. We've just seen that the odometer checks against the road markers, so we won't need them anymore. And now that we've calibrated the odometer, we can use it to check the speedometer. Okay, I'll start the charts. There we go. Now I'll try to hold a speed of 36 miles an hour during this test. 36 miles an hour is 0.01 miles per second. That means I go 36 miles every hour. In 1 second, I go 1/100th of a mile. In 10 seconds, I go 1/10th of a mile, and so on. Now, there I have it. If you watch the pen trace, you'll get a better feeling for how steadily I'm able to keep this speed. It's wavering around 36. Hold it as best I can for a few more seconds. Meanwhile, my odometer is climbing in a straight line, marking the distance. All right, now I'll begin to slow down. And now, as a check on the speedometer against the odometer, let's see what we can find out. Here's the interval where we tried to hold a steady speed of 36 miles an hour, 10, 20, 30, 36. Notice that in this 20-second interval, the speed was fairly constant. Let me transfer 20 seconds then from this curve to this curve, our odometer curve. That's this corresponding interval here. In that interval, I should have gone exactly 2/10 of a mile. At the end of the interval, I was up here. At the beginning of the interval, I was down here. And if I set this on and read the scale, I get 0.198 instead of 0.200. But that's within 1%. And again, we've checked out pretty well. Now let's look at our accelerometer. We've just discovered that we have a good speedometer, so let's use it to check. Now notice that as I accelerate, the accelerometer reads positive. Now the accelerometer has come back to 0. Now that doesn't mean that I've stopped. As a matter of fact, if you look at the speedometer, you'll notice that it reads a steady 21.5 miles an hour. And in fact, if you look at the odometer, you'll see that it's picking up distance at a constant rate, and in fact 21.5 miles every hour. Now let's come to rest. And notice that when I decelerate, the accelerometer goes negative. And now I'm at rest. And now I'll try calibration. I'll come up at a constant acceleration, like this. Hold my speed a little while. Notice that the accelerometer again returned at constant speed. And now I'll try to come down on the brake in such a way as to give me a constant deceleration like this. And now we're at rest. Let's look at the data just as a rough calibration of the accelerometer. Here's the interval where we were running at low speed, and here's the interval where we were calibrating. If I lay a straight edge along this slope, which is, as you can see, quite constant, and then estimate, by shifting a little bit here, how many miles per hour I changed in 5 seconds, I get almost exactly 40, which means 40 miles per hour in 5 seconds, or 8 miles per hour per second. The calibration here is 2 units per division, 2, 4, 6, 7, and almost 8, which is a check. If I want to look at the deceleration, here I am with this slope, and shift that a little bit, parallel. In 5 seconds, I came down approximately 25, so that should be 5 miles per hour per second. 2, 4, 5. So we have, in fact, checked our accelerometer, and we have a complete set of instruments. Well, now we have 3 meters that we know that we can use. And from now on, we'll look at all 3 at once. We'll take the trip that we talked about at the beginning of the film. First, you'll notice that I have drawn baselines on the 3 graphs to represent the 0 positions of the pens. Now, I'm going to make the trip in 2 parts. The first part I'll make as simple as possible. Let's start the charts and go. I'd like to hold a steady acceleration up to about 35 miles an hour. Now notice that I've stopped accelerating and that I'm holding a constant speed. And after a little bit of this, I'll come to the end of the first part of my trip by slowing down like this at a constant deceleration. That was as good as I could do. Now for the second part of the trip, I will try to do an erratic set of accelerations like this. Up to a high speed, which I'll hold for a tiny bit. Start a series of decelerations, again erratically, on the brake, and then a few birds like this, to give us a complicated trip. And finally, to rest. Now, here we have a complete record of this trip from the standpoint of distance, speed, and acceleration. And the only thing I'm going to say about these curves right now is something that might surprise you a little bit. I could have taken any one of them alone without the other two. That is, I could have just measured this one, or this one, or this one. And then in principle, I would have just as much information. That is, I could derive the other two curves from any one of them. Well, our next job, of course, will be to see how this can be done. Suppose we had only the distance curve. In fact, suppose that the curve of d against t had a little section in it that looked like this, a rising straight line. Now, what I've been telling you is that from this, we should be able to get v and a. Out on the road, we notice that whenever this happens, we have constant speed. So right away, I know that. Over that interval of time, constant v. But how do I get the value of the speed? Well, that is simply the slope of the d curve. Delta d over delta t. This is the key idea in going down the page, the slope. And in fact, I write delta d over delta t, and I call that v. Now, notice that that slope, defined that way, doesn't depend on where I go on the interval. I could have measured it there, and I would get the same ratio, and that tells me I have constant speed. Next, let's suppose that we come to a stop. We remember that what that did to us on the road was to give us a d curve which levels out, let's say like that. Over that interval of time, the slope is decreasing and reaches 0. So I know that the speed must do this. And now I'll go to the acceleration using the same kind of rule. I draw myself these axes, and I ask what happened to the slope of v. First of all, what I mean by that is again a ratio, but this time delta v over delta t, and I call that a. Here the slope is 0 until this time. It becomes 0 again here, and in this region it's negative. Delta v is negative, the slope is negative, the curve is falling. So I know I have a negative acceleration. In fact, here's a region where the slope is fairly constant, so I have a constant negative acceleration, which started from 0 and ends at 0. And that's then how we do it, from d to v and from v to a, by taking slopes. Well, does this really work? Let's try it out on the records that we made in the car. Here they are. All I've done to them is to add scales, miles, miles per hour per second, and I've laid them one above the other so that the time scales, which I've added here, will correspond with each other. And now let's look at the slopes of the d curve in a general way. Here's a region that looks like what we just did on the board. Fairly constant slope, then coming back to 0 slope. And the corresponding speed, fairly constant, and come down to 0 speed. In this region, the thing is complicated. We have a slope which hardly ever stays constant, and a speed which hardly ever stays constant. Now let's measure a slope. First, let's look at this region of the curve, and let's use this drawing engine, which is just a device for holding a fixed angle. That is, I bring my edge up to the curve like this, and then lock the angle like that. And now if I were to draw the line whose slope I'm trying to measure, and now the engine permits me to bring that down to another place where it's easier to read a slope, say here. I'll read it off. We can let delta d be this interval, 1/10 mile, delta t 10 seconds. So the slope is 0.1 over 10, or 0.01 miles per second. The speed that we read here is 36 miles an hour, and you'll recall that that is 0.01 miles per second. Now we look at the more complicated regions of our curves. Here we don't have any straight line portion to speak of, so we can't measure the slope quite so easily. Well, we simply have to realize that the direction of the curve at any point is the direction of the tangent line. Let's therefore look at the tangent at 60 seconds. It would look like this. And if we wanted the slope, just measure the slope of that tangent line. A little while later, say there, we would draw this tangent line, and so on. Now let's draw the tangent line at this point and actually measure it. It looks like this. I bring it down to a convenient place, and I read in 10 seconds a change in distance of 0.14 miles. So that's a speed of 0.014 miles per second at this time. Coming down to our speed curve, we see the time is 70 seconds. And at 70 seconds, we had a speed of just about 0.015, whereas we predicted 0.014 from the slope. Now we shall look at the relationship between speed and acceleration from the same point of view. The rate of change of speed gives us the acceleration. In this region, we have roughly what on the blackboard, a region of constant speed falling off to 0. When the speed was constant, the slope was close to 0. Here, notice the acceleration is close to 0. Then we had a negative slope in the speed curve, and here's the negative acceleration. And finally, a 0 slope, 0 acceleration. Now, in the more complicated region, we had many fluctuations in the slope of v, and we see them all showing up in a very beautiful way as rises and dips in the acceleration curve. Notice this one. Here's a very small change in the slope where I let up on the gas, giving us this dip at exactly the same time in A. Here the slope also decreased, and it shows up here, and so on all the way through. Here's a place where the slope became positive again, and we expect a positive acceleration, and there it is. So that's the way the curves look. Now, to make an actual measurement, I'd like to take a place in the complicated region and look at one of these slopes accurately. Let's go to 80 seconds and measure the slope right there. I bring the drawing engine up to the curve just at that point and draw a tangent like that. And I'm going to measure the slope of that by bringing it over here and seeing how far the curve changes in 5 seconds, which is this interval of time from here to here. Well, I get a change of 10, 20, 30 miles per hour in 5 seconds, and that's an acceleration, a negative acceleration, of 6 miles per hour per second. So we come down to our acceleration curve at 80 seconds, and we read, recalling the calibration of this, -2, -4, -6 miles per hour per second. Now we know how to go down the page, taking the slope of the distance curve to give speed, and the slope of the speed curve to give acceleration. But now suppose we want to go up the page. Suppose all we had was the acceleration curve. There should be something about this curve that tells me something about the speed. Well, I can't take the slope anymore. Clearly, I have to do something new. And a property of the curve that I can start to study is its area. In fact, the answer is that the area under this curve, say from the beginning out to here, gives me at the same time the change in speed from the beginning of the speed curve. Suppose I didn't have the distance versus time curve or the speed curve. but that I did have the acceleration curve to begin with. The problem is, can I construct the speed curve from it? Well, here's a relationship that we know, and notice that I can transpose it to read A times delta t equals delta v. Acceleration times the time interval gives the change in speed. Also suppose that this were simply a rectangle. Then this quantity is just the area of the rectangle. And suppose the acceleration were 5 miles per hour per second, and the delta t were 10 seconds. I then have an area of minus 5 times 10, which is 50 miles per hour. And that must be the decrease in the speed over that time interval. If, in addition, I know that the final speed is 0, then I know that it must have started at 50, and the speed curve would look like this. Now I'll go on and try to construct the distance curve from the speed curve. And I'll give myself a new problem. I don't need this anymore. And if I make a trip complete, I would perhaps start at rest, build up to this, and then decrease. Now clearly I want the area of this, because I have the same relationship here that I had here, and that area will give me the change in distance. Well, let's take a rocket problem, one that used to be recherche but isn't any longer, a rocket to the moon. Suppose v were 6,000 miles per hour, which is the reasonable average speed, and the delta t were 40 hours. The product, which is this area, is then 240,000 miles, which we know is the distance to the moon. And that tells me that the net increase in distance, let's say starting from 0, is 240,000 miles. Well, we'll try this idea out on our curves. First, I'd like to measure this much of the area of the A curve, the part I've already cross-hatched. And the answer should give me this much change in speed, which is 36 miles an hour. Now, there are several ways in which I could try to get an estimate of the area. For example, I could count the squares under the curve, or I could cut it out and weigh it. What I'll do here is to notice that the shape of this curve suggests that I approximate it with a triangle, drawn like this. I suggest that the area of that triangle is equal to the area under the curve. The base of the triangle goes from about 7 seconds to about 25 or 26, about 18 seconds. The height is about 4 miles per hour per second. The area is a half of the product of those two. A half of 4 is 2, and times 18 or 17 is 35 or 36. Just exactly what we expected. Now, this procedure can be used all through the A curve. When we do this interval, we're getting a negative area, reminding us of what we did on the blackboard. It gives then a decrease in the speed from here to here. And in fact, since we return to 0, we must have an area here equal in magnitude to the area there. When we go into this region, we have a new increase in the area, and therefore an increase in the speed to here. And this region will give us an additional increase in the speed from here to here, and so on to the end of the curve, ending with a 0 total area for the entire acceleration curve. And now, if I want, I can look at the speed curve from precisely the same point of view. Look at this area. I can take v, like this, and delta t, like this, and suggest that the area of this rectangle approximates the area under the curve out to this time. That should give me the change in d from here to here. I won't do this for you, but I'll point out that if you do it for yourself, you'll find that it's extremely accurate. When you get out into here, you may wish to use triangles. In fact, this whole bit can be approximated with the area of this triangle. And that should give me the additional change in distance from here up to there, and so on to the end of the curve. In fact, the entire area under the V curve will give me the net change in distance over the entire trip. And so with our area rule, we can see that if we started with only the acceleration curve, we could generate the other two. And now it might be interesting to watch these curves being made again, just as they were in the car. I've enjoyed playing with them, and perhaps you will too. You'll begin to notice that there are more things to the features of these curves than we have so far mentioned. For instance, there are errors in the instruments. Look at the part of the curve now being generated. The speed is roughly constant, the acceleration is roughly zero, but when we look a little more carefully, we see that really the speed is decreasing slightly, therefore has a negative slope, and the acceleration, on the other hand, is slightly positive. Now, you know as well as I do that that's just plain wrong. It's an error somewhere in the instruments. And the interesting thing is that we know it has to be a mistake. We started out with the idea that we were taking three separate measurements of three separate things. But now we know they're not really independent. They are governed by relationships that we call their definitions. So, insofar as the meters are accurate, any one of these pens is making a complete record of the trip, and the other two are merely slavishly following along, carefully relationships that we mean when we talk about distance, speed, and acceleration.